Good afternoon, speakers, ladies and gentlemen. Welcome to the second session of the Urban Noise webinar series, Digitalization of Urban Noise Sensing, Noise Control, and Soundscape Technologies. This event is jointly organized by Nanyang Technological University, NTU, and Housing and Development Board, HDB. My name is Kelvin. I'm from the Building and Research Institute, HDB, and I'll be an MC for today. For those who are yet to register for the third session tomorrow, you may do so via the QR code shown on the screen now. During the webinar, if you have any questions, please feel free to submit them via the Q&A icon shown on your device. You can also upvote questions which are of interest to you by clicking on the thumbs up. Our panelists will be answering some of the more popular questions at the end of the talks. In today's sessions, we'll have two speakers with us to share on some of the more latest development for active noise control technologies and its potential application in the urban environment. For our first speaker today, we have Professor Masaharu Nishimura, who is currently the president of NLab, a machinery noise consultancy firm in Japan. Professor Nishimura has since retired from Tottori University in Japan and was previously at Mitsubishi Heavy Industries for 30 years prior to his academic appointment. Professor Nishimura's research interest is on active noise control, notably on active noise barriers and active acoustic shielding for apertures. He also has extensive experience in noise control for machinery, in particular air conditioners and construction machinery. Today, he'll be sharing on a trial of mitigating floor impact noise by ANC technique and other ANC topics in the construction field. Professor Nishimura, please.
Masaharu Nishimura from Japan. I'm a former professor of Tottori University and now the president of NLab, Machinery Noise Consulting. It's my pleasure to talk about our research on active noise control for floor impact noise and other topics in this webinar. Here shows the contents of today's presentation. After talking about basic concept of ANC, I'd like to talk about ANC for floor impact noise, the main theme of this presentation. After that, I will introduce active noise barrier and ANC for construction machine in Japan. At first, the basic concept of ANC. ANC is defined as changing a system sound field by actuator like speakers and controlled based on signal measured by sensors, microphone. ANC can cancel the primary sound by the anti-phase secondary sound. It can change the characteristics of sound field, such as damping, resonant mode, etc. And ANC can also change the boundary condition of sound field, such as sound absorption coefficient and transmission loss, and so on. ANC is effective for low frequency noise because the controllable zone by one channel system is proportional to its wavelengths. Generally, ANC is said to be effective below around 500 Hz, and in higher frequency region, some passive method is effective. ANC has two important points. One is how to realize the anti-sound field, which has same gain and anti-phase is as primary one by control speakers. ANC is considered to be superposition of primary sound wave and secondary sound wave. This determines the appropriate placement of control speakers and error microphones. Here shows the example. Point sources installed at appropriate interval can generate inclined plane wave. The second important point is how to realize the above control by realistic signal processing software and hardware, satisfying causality and cost performance. ANC can use both feed-forward control and feedback control. From here, I'd like to talk about ANC for floor impact noise. Floor impact noise is one of the important problems bothering our comfortable life. Low frequency sound component below 63 Hz is dominant, as shown this figure. This figure shows a typical sound spectrum of floor impact noise, this spectrum. And these lines show the rating curve. As you can see, low frequency noise determines the rating, floor impact noise rating. Normally, passive countermeasures such as adding mass, rigidity, and or damping of the floor are applied to reduce its vibration. Some active countermeasures have also been tried. One is to suppress the vibration of ceiling plate like this. This was tried to be developed in Ritsumeikan University in Japan. In this case, noise insulate panel are installed under the slab and actuated by moving coil type actuator to reduce their vibration, as shown here. It could reduce basic vibration, basic mode vibration of the panel. However, it is difficult to reduce higher mode vibration. The other trial is to increase the transmission loss of the ceiling, like this. This was experimented in Tottori University. In this case, sound transmission loss is increased by reducing the sound pressure between the two panels, which is upper floor and ceiling, with large speakers. We can reduce the sound pressure in this zone. As you can, these graph shows the experimental result. As you can see, it can reduce the transmitted sound in low frequency region. This system was proved to be feasible by model test. However, too many large speakers are needed in this case. Then we tried to mitigate floor impact noise by ANC in receiving room. Here shows a typical sound spectrum of floor impact noise in receiving room. As you can see, there are many peaks in low frequency region. These peaks are caused by the acoustic resonance in the receiving room. In the case of steady noise, these resonant noise can be easily reduced by ANC with feedback control. So the issue is this ANC technique applicable to impact noise? We conducted some experiment using floor impact test room. Receiving room is 4.35 meter wide and 7.5 meter length long and 2.7 meter high. Walls are made of concrete with thin sound absorbing materials. Test floor 3.6 meter wide and 1.8 meter length is installed at the open area of the ceiling and is impacted by bang machine. This is receiving room, photo of receiving room, and this is a source room with bang machine. This shows a relative sound spectrum excited by the bang machine measured in the receiving room. This peak of 22.5 Hz corresponds to the first mode in the receiving room, 010. And this peak of 45.2 Hz was found to be consist of two modes, 110 and 020. The eigenfrequency of those modes are very near in this case. This slide shows the test condition. Four control speakers and 4 air microphones are installed at the four corners on the floor in the receiving room. And 4x4 feedback LMS algorithm were applied. The sampling frequency is 3 kHz. It's rather high, aiming for rapid convergence. And the control filter are fixed after adaptively converged. Noise reduction is evaluated by the average value of peak average spectra of 5 times of impact at 5 monitor points. This photo shows a control speaker and error microphone here. This graph shows measured spectra at error point. It's 1H, one of error point 1H and monitor point L1 here. In the condition of ANC on and off. You can see both points at both points, every peak spectra are reduced, especially low frequency peak spectra are reduced by around 10 decibel by ANC effect. Especially, I would like to say the peak spectra around 20 Hz is reduced remarkably. It's not audible, but feeling of sound became light, not reverberant by ANC. This shows sound wave pattern of the impact noise. ANC off is blue line and green line stands for the ANC on. As you can see, reverberant waves are rapidly reduced by ANC. This effect seemed to reduce noisiness of floor impact noise. This is evaluation chart of floor impact noise. In this case, band noise of 63 Hz was reduced by 3.5 decibel with ANC. And the rating of floor impact noise is improved from L70 to L65. In conclusion, for floor impact noise, generally, floor impact noise has high intensity peaks spectra at resonant frequencies of the receiving room. Those peaks can be reduced by ANC in the receiving room. Multi-channel feedback LMS algorithm is effective for reducing reverberant sound wave of the floor impact noise. As a result, the rating of floor impact noise was improved by 1 rank. Next, I'd like to talk about active noise barrier. At first, active soft edge AC. AC has many AAT cells, which is AAT means active acoustic treatment. Many AAT cells set in a line on the top of the noise barrier. AAT cells control the surface sound pressure, that is edge potential, this part, to be zero by the analog feedback controller. This system concerns only sound pressure at the surface of AC. It does not concern the direction from where the sound propagated. As a result, diffraction sound is reduced. It is effective not only for a stable single sound source, but also for multiple moving sound source. In this case, 2 AAT cells are installed in the one section. Each AAT cell is controlled individually by analog feedback controller. In this case, the flow resistance of facing sheet is very small, and the sound reflected coefficient become -1. That means sound pressure become 0 at the surface of AC. We call it acoustically soft condition. So we call it active soft edge. This slide shows the noise reducing effect of AC for stationary sound source. We performed an experiment in this configuration in the open field. A noise barrier with AC of 3.25 meter height and 20 meter length was installed. This graph shows the A-weighted sound pressure spectrum measured at this position. Black line stands for the case without noise barrier. The spectrum pattern is shaped similar to general traffic noise. Blue line is a case of normal barrier. And the red line shows a case of AC. Here, the sound is reduced by active effect below around 1 kHz and by the passive effect over 1 kHz. This slide shows the effect of AC for moving noise source. The speed is 60 km/h. Red line shows the case of ANC off, and blue line shows the case of ANC on at 500 Hz 1/3 octave band frequency. You can see AC is also effective for moving sound source. AC has been installed along a real road more than 15 years ago. Since more than 15 years ago, this is a photo of Route 43 in Japan. These are AC. AC uses an analog controller, but advanced active noise barrier AANP, which uses high-speed digital feed-forward controller, has already developed. AC can only attenuate the deflection sound, this zone, and the control frequency range is rather narrow because of analog feedback controller. Moving multiple sound source can be reduced by AC. On the other hand, AANB is decentralized ANC by a digital feed-forward control. It can attenuate sound of target direction, such as this direction. Control frequency range is rather wide because of feed-forward control. And moving multiple sound source can also be reduced if the distance between the reference microphone and the control speaker is very small, as shown here, like collocated. This is important point. Active acoustic partition, AAP, is one of the applications of ANB. In this case, active noise control of dual direction is necessary. We performed the basic experiment in a normal room. 4 sets of control speakers were installed in array on the top of partition. Every set of control speaker has one reference microphone on each side. So there are totally 2 reference microphones in every set. 4 error sensors set on each side, and they were only used during converging the control filter. Double 4-1-1/4 feed-forward control algorithm was applied to converge the control filter. The control filter were fixed after converged, and the error microphones were removed. These are photos of experiment. Here shows the effect of ANC of error microphone of right-hand side. Similar effect was obtained in left-hand side. So you can see the appropriate noise reduction is obtained in both sides, like this. Finally, I'd like to introduce some example of ANC for construction machine in Japan very briefly. This is active noise barrier for stable noise. Stable noise source produced by ANC engineering. These are control speakers. This is controlled by feed-forward algorithm and increase noise reducing performance in low frequency region. This is noise source and reference microphones and control speakers, and error sensor is here. This shows the noise reducing effect for diesel generator. You can see noise reduction is obtained from 50 Hz to 200 Hz with ANC. This slide shows ANC for engine exhaust noise of construction machine produced by ANC engineering. In this case, the exhaust duct is installed to the cover duct, which has control speaker and cooling fan. The exhaust noise is reduced inside the cover duct by feedback control. Here shows noise reducing effect. You can see the combustion noise is reduced remarkably by ANC here. This is also ANC for engine exhaust noise of construction machine produced by Toda Corporation. It's called tank system. In this case, the duct exit of control speaker is set near to the exit of engine exhaust noise, engine exhaust duct. This system is also controlled by feedback controller. This is dual speaker system. These are the exit of control duct, and this is the exit of engine exhaust duct. This slide shows the effect of tank system. As you can see, low frequency combustion noise at 63 Hz is remarkably reduced, not only error microphone, but also far field. Okay, that's all my presentation. Thank you for your attention.
Thank you, Professor Nishimura. I'd like to encourage the participants to post your questions using the Q&A button. And remember to upvote those questions that are of interest to you. Next, we have our second speaker, Professor Woon Seng Gan, Director of Smart Nation Lab at the School of Electrical and Electronic Engineering, NTU, Singapore. Professor Gan's key research areas are centered around sound perception and audio engineering. One key focus is on active noise control, which has resulted in a proof of principle prototype for the control of urban noise through an open window. He'll be sharing further on that in his talk today, active noise control and its application for mitigating noise through open window. Professor Gan, please.
Hi everyone, welcome to the second day of the webinar series on urban noise. My name is Woon Seng from NTU, Singapore. Professor Nishimura has given us an interesting account on the active noise control research and deployment in Japan. It's indeed exciting to see many great developments of ANC techniques applying to the building and construction sectors. So my talk today is also follow Professor Nishimura's theme on active noise control application, and I would like to describe our work carried out in NTU on mitigating noise through open windows. This work is also in close collaboration with Professor Elliott and also with Professor Nishimura. urban noise. I believe everyone is familiar with this type of urban noise they experience daily. World Health Organization call it the most underestimated threat that affect both the short-term health problems like sleep disturbance, annoyance, affecting attention, to a long-term health problems like heart disease, hypertension, hearing impairments. So there are growing evidence from several studies that shows noise has a negative health effects. So in the European studies on annoyance from transportation noise, a 10 decibel reduction also has a significant impact on the noise annoyance. For example, a reduction from 75 decibel of aircraft noise to 65 dB of aircraft noise will reduce the annoyance percentage of annoyance by 50%. So therefore, there is a strong correlation on the perceived loudness and the annoyance. So it's also significant to note that to achieve at least a 10 dB of noise reduction is a very significant steps to take. So in a 2014 Lancet paper, reported a meta-analysis where a 10 decibel reduction in equivalent transportation noise exposure will be translated to a 7 to 17% decrease in associated health risks, such as hypertension and heart disease. So what is the main contributors of noise pollution? A comprehensive study in Europe shows that the main culprit comes from the road traffic noise at around 88% due to the proximity to the residential areas. This is followed by less than 12% coming from the rail traffic, the air traffic, and the industry combined. So it's also interesting to see that there are several recent article headings starting to equate the ambient noise to secondhand smoking. So people are now taking noise exposure more seriously, and there's a growing concern in noise pollution in our urban environment. So based on the European data, most of the mitigation measures are mainly focused on social economic measure and promotion and awareness, around 29%. This is followed by road traffic management at 25%, and the measure at the propagation path, for instance, erecting noise barrier at another 25%. However, there are only a few implementable measures at the receiver end, which is sometimes the only viable option for noise mitigation. So the sketch on the right-hand side illustrates the three main components of noise that can be addressed at the source, at the path, and at the receiver. The best approach whenever possible is to reduce the noise emitted by the source. So improvement in the source design can achieve a significant reduction in emitting levels. As an example of traffic noise, design improvement can be made to the automobile mufflers or make changes to the traffic pattern controls. The noise path can be addressed through structures such as berms or noise barriers. If a human listener is at the receiver position, they can use hearing protectors to reduce their noise exposure, or through an active control method that I'll be showing you later. So the usual medium in high-rise residential buildings may not be that effective. So as noise can be diffracted over the top of the barrel, adversely affecting those staying in the upper floor of the residential building, or some of the lower frequency noise can also penetrate through the barrels. By simply increasing the height of the noise barrel will block out natural ventilation and light into the lower floor of the residential building and may not be a cost-effective solution. So finding a suitable and practical solution for controlling noise into the natural ventilated buildings is a challenging problem. Our proposed approach takes into the following consideration. First of all, in the context of urban high-rise situations, we propose an approach to control noise at the receiver end, targeting at the point of entry of noise, which is the open windows. Second, it's known that active control solution using the principle of superposition is only effective at lower frequencies. And most of the traffic noise energy is in the lower frequency range below 2000 Hz. However, this proposed strategy should also maintain the window functionality, especially for natural ventilation and access to natural light. So in my today's talk, I will look into the active noise control technique. How does it differ from the passive approach, which uses material to shield off the noise source? Also, a lot of us has now been using active noise control headphones or earbud like the one you've seen here from Apple AirPods Pros during this period of working from home and conducting virtual meeting at home. So how does this type of active noise control technique, which is used in our earbuds, is scale up to active noise control windows? So I will showcase some of our recent R&D prototypes developed in NTU and the latest published result in this talk. To start with, why digital active noise control? Digitization of sound signals provide us with immense flexibility in manipulating and analyzing the sound signal, which would otherwise be impossible to achieve in an analog solution. So if you look at the traditional passive approach of noise control, for example, using noise barriers as shown in this diagram, they are considered as a passive technique as they only rely on passive material. They are thick, exhaustive, and work effectively well at higher frequency noise. But they are usually large, block out airflows, ineffective at low frequency. Earplug is another passive control example. Active control, on the other hand, uses the electroacoustic or electromechanical system to generate a destructive interfering sound through the noise and operate effectively at the lower frequency below 2000 Hz. These actuators are usually referred to as a secondary source. So we have also seen several active noise control examples from Professor Nishimura talks, such as the soft edge ANC units that's been installed on top of the noise barrier, and also using ANC to cancel out the exhaust noise coming from the construction machineries. To put it simply, ANC needs a secondary source to emit the anti-noise so that it can counteract the noise and is effective at handling noise at lower frequency below 2000 Hz. So how does ANC works? It works on the principle of destructive interference of noise. So as mentioned, ANC must emit an anti-noise at the same frequency as the detected noise, but with inverted sound wave to cancel out the annoying noise. This is shown in the animation below, where you have a purple sine wave that denotes the noise, and the brown signal is the anti-noise that's produced by the actuator, okay, which is inverted in phase to the noise. So anti-noise destructively cancel out the noise. In physics, we call it the superposition principle, where sound wave sums up in air. So the generated anti-noise must be emitted such that it matches the noise wave in air, both in time and in space, so that the timing of when to emit anti-noise and the location to achieve good cancellation is very important in active noise control to work effectively. So if you denote the primary source as X, the anti-noise or the secondary source as minus X, so we can achieve 100% noise reduction with zero noise residue, as shown in this simple max equation. So 100% cancellation is easily said than done, as any amplitude timing mismatch will result in a residue noise, as shown in this diagram. So over here, this is a perfect matching where you have no residue noise at all, as shown by this equation. But once you have amplitude mismatch, this two sine wave doesn't match up in the amplitudes, residual noise starts to creep in. If you have a phase mismatch, residual noise also starts to come in. So we can further elaborate by this simple equation, which states the noise reductions of the by matching the two sine waves. So the perfect cancellation is where the wave matches 100% in amplitude and phase, and this is at the location at the origin. So we don't have any phase errors or no amplitude error. We can achieve 100% reduction or minus infinity dB. But once we have a slight variation of the phase errors and amplitude errors, the noise reduction performance degrades. For example, a mere 1.8 degrees phase difference and a 0.1 dB amplitude offset will result in the attenuation of just minus 30 dB. So when the phase and amplitude error get bigger, we will at the expense of a reduced noise reduction. So this slide shows the current commercially successful ANC applications, which include the ANC earbuds, the ANC headphones, and ANC is also used in automobile to cancel out engine noise and also the road noise in the automobile. So how do we extend the ANC headphones into an ANC window? So ANC window works on the same principle as active noise control headphones, but it requires us to distribute the secondary source across a much bigger region, across the window opening to achieve a wider region of noise control, instead of just confining the noise control around the ear as in the headphone ANC. So let me show you the basic electronic components of the ANC headphones to start with. So as mentioned, an active control is based on the wave superposition, where the secondary source, usually a loudspeaker, is used to generate the destructive or anti-noise wave to attenuate the noise that leak into the ear cup of the headsets. Okay, so that we can reduce the noise that's coming into the headphones. It requires a reference microphone, as shown here, denoted in 3, to pick up the advanced information of the noise source, so that this signal can be passed into a digital controller to predict and compute the destructive wave, what we call the anti-noise. So feedback from another microphone, known as the error microphone, shown here in 2, is used to provide the information to the digital controller on the changing characteristic of the disturbance noise. As mentioned, ANC need to generate anti-noise at the right time for ANC to work properly. But you have this delay incurred by the analog to digital components as well as the digital controllers. So this electronic delay must be shorter than the acoustic delay in order for the active noise control to perform well. So this is what we call the constraint of causality, where the acoustic delay is the time the sound signal comes from the external into the ear cups must be longer than the electronic delay it takes to compute the anti-noise. Note that the ANC headphone also have a passive component, which is the ear cup. And this passive component is basically cancel out the high frequency noise. But the low frequency noise will still leak into the headphones and still will need to be cancelled out by the active noise control system. So it's also important to note that this ANC headphone is only concentrating the noise control around the region of the ear. So as noted, the ANC headphones only deal with noise control around the ear. But how do we deal with a much bigger surface of noise control? So for ANC windows, we need to adopt a slightly different active control strategies. The complexity of the building an ANC window is now much higher than the ANC headphones. as we need to take care of a larger region as mentioned. The ANC windows therefore require multiple of these secondary sources that can be distributed across the opening to provide us with sufficient anti-noise to cancel out noise in the opening of the windows before entering the room. So for this reason, the computational complexity of system is much higher, and higher end processing capability is needed to sample the noise sample at a very high frequencies to meet the causality constraint as explained previously. So for ANC windows, we are basically containing the noise at the window opening and reducing the noise intensity before it enters the room, and thus result in a global noise control inside the room. So when people are inside the room, they will not need to wear any hearing protectors. The noise reduction is basically taking place at the opening of the windows. So also taking note that there's no passive material used in the ANC window, as we do not want to compromise on the natural ventilation and access to light. So there are generally two categories of active strategies for controlling noise through the apertures. The boundary layout as shown on the left, where control sources, the secondary sources, are distributed around the entire boundary of the apertures. Another layout approach is using the distributed layout, where control sources are distributed across the entire opening. So today, we will focus on the later active control strategy, which is based on the distributed layout. So in ANC, it's important to understand the physical characteristic of the active control system. So each ANC problem is unique. For example, ANC problem for car, automobile is different for ANC approach to headphones, etc. And as you can see from this chart on the right, the arrangement of the control source determines the maximum amount of noise attenuation. So it's important for us to pay a lot of attention on how do we arrange the control source around the region of noise reduction. So we will have to make use of some acoustic simulator to help us to understand the best control source arrangement for ANC windows. So in our work, we adopt a numerical 2D simulators for us to evaluate the placement of the secondary source. So this 2D numerical simulator provides us with a very useful tools to understand how multiple secondary sources will behave under different noise field. So the simulator will allow us to examine the different parameters in determining the effective physical interspacing of the secondary sources, sensors and secondary source placement under different direction of a primary noise coming into the windows. Over here, you see a series of simulations carried out for noise control of 500 Hz with an incident angle of 0 degrees, and the one at the bottom is 500 Hz with an incident angle of 30 degrees. Over here on the right, you see the noise source is changed to 1000 Hz. So you will see that when the active noise controls takes place, the secondary source will fire up the anti-noise, and the anti-noise will interact with this noise and reduce the intensities of the noise before entering the room. So Dr. Lamban has been working on this simulation and experimentation for his PhD. So his PhD thesis outlines several important equations on how we select the number of secondary sources and the placement of the secondary sources. So he has derived this optimum number of control sources with reference to the angle of incidence. So here N denote the number of secondary source needed for a window size of L in terms of meters for noise coming in from different angles from 0 to 90. Okay, so with this equation, it will give us an upper bound on the number of secondary sources that we require for us to apply the active noise control techniques for windows. So in order for us to validate the simulation results, a test chamber is built So in this case, you see that we have a test chamber of 2 by 2 by 2 meter cube was constructed and placed into recording studios. So a full-size sliding windows of 1 meter by 2 meters was installed at the front end of the test chambers to conduct a proof of principle experiment. So we built a 24 channels active noise control. These 24 channels consist of 8 rows by 3 columns grids and attached to a grill inside the windows, and the microphones are facing outwards towards the noise source. This forms a planar array of control loudspeaker distributed across the entire windows. It will emit the anti-noise towards the interior of the room at the same frequency but opposing pressure patterns of the incoming noise. So to essentially cancel out the intruding noise. So this is the dimension of the secondary source. The secondary source is a 5 cm in diameters and with a length of 12 cm. So this is a photo showing you the interior of this 24-channel ANC system. It's attached to a grill, 8 rows by 4 and 3 columns. And this is the external view showing you the microphone that's facing outward to receive the advanced information of the intruding noise. So a cross-sectional view of the active control system is shown in this block diagram. So noise is impinging from the left to the right. Reference microphone sense the noise and provide this advanced information to a digital controllers. And the secondary source generates the anti-noise wave to cancel out the disturbance at the error microphones, which provide this feedback of information to the digital controller so that it can adjust the coefficients, adjust the controller to match the incoming noise. Ultimately, our target is to achieve a global noise attenuation in the interior of the room without obstructing much of the natural ventilation and lights. So what are some of the R&D results that we have carried out in NTU? So next I will describe some of these recent results and some of the key performance indicators for our noise control. So our latest proof of principle study has just been published last month in the Nature of Science scientific reports. Okay, so the information of this publication is shown in these slides. In order for us to measure the global noise reduction inside the test chamber, we use some 18 microphones are placed at different locations around the interior of the test chamber according to the ISO recommendation. We evaluate the energy average sound pressure at the entire room and also the planar average sound pressure around the opening of the windows. So the left diagram shows the cross-sectional side view of the test chamber, indicating the microphone heights. And the right diagram shows the cross-sectional top view of the microphone placement within the interior of the test chamber. So microphone 1 to 12 arranged in a rectangular grids, which is 0.5 meter away from the opening of the window, will measure the planar average sound pressure level. Microphone 1, 13, 14, 15, 16, 17, 18 are used for computing the energy average sound pressure level inside the room. So let me show you some results after the measurement. This table shows the energy average sound pressure level highlighted in red and the planar average sound pressure level highlighted in blue based on the selected microphones arrangement shown in the previous slides. So we test the ANC for broadband white noise, highway noise, train noise, and aircraft noise. And the frequency range is from 100 to 1000 Hz. Okay, so we compare this ANC performance with a passive attenuation that is a fully closed window. So we can see there are some 2 to 5 dB of noise reduction difference between ANC windows and the full closed windows. Okay, also we note that the ANC window can achieve 7 to 10 dB of energy average sound pressure level reductions, as well as 8 to 11 dB of planar average sound pressure reduction. Since the difference between the average and the planar is basically less than 1 dB, global attenuation was achieved in the room interior. Effectively, there's little difference between the noise reduction performance at the opening of the windows and the interior of the room. So our ANC systems were effective from 300 to 1000 Hertz. So this is a range encompass most of the traffic and train noise. Although the small speaker that we use limit the mitigations of very low frequency below 300 Hertz. Okay, the result stated in this slide shows the energy average sound pressure level coming from the broadband noise, the highway noise, train noise, and then the aircraft flyby noise transmitted through an open window. The thick solid line shows the ANC turned off before any ANC being deployed. Okay, turned off. And the dashed line shows the effect when ANC is turned on, the dashed line over here. While the thin line is the reference where the window is completely shut or closed. So from this plot, we can see that our ANC system starts to attenuate noise from 300 Hertz to 1000 Hertz with a 10 decibel of energy average reduction. In some frequency bands, our ANC is as good as closing the windows. We also perform a moving energy average sound pressure level for some of the non-stationary noise like train noise and aircraft pass-by noise before and after ANC is deployed, and with window fully shut as a comparison. This is the time domain plot to highlight the noise reduction performance during the time period of noise occurrence. So a uniform attenuation of the noise can be seen in these moving average plots, where ANC can perform a good job in responding to a non-stationary noise patterns. So the spectrograms also shows that the key noise components around the 700 Hertz is being cancelled out by the ANC window. Okay, so and so this is quite a distinctive cancellation being performed by the ANC windows. So to further investigate the performance of active noise control system, we use an acoustic cameras with calibrated condenser mics to measure the real-time performance of the noise reduction. So the measuring device allows us to understand the spatial noise reduction across the window opening. Please note that the open window is located at the right-hand side. Okay, this is the open windows. And the one on the left-hand side is completely closed. Okay, as this is a sliding window setup. This video shows the acoustic camera in action when the ANC system is turned off and the band-limited noise from 400 to 1300 Hertz is generated from the outside of the test chamber. So let me play this video. So you notice that the sound pressures at the opening is around 65 decibel. And the acoustic camera basically pinpoint where is the majority of the noise energy coming through the opening windows. Okay, it's basically denoted by the lighter patch, lighter white, yellow patch over here. So now, when we turn on our ANC system, we will see what happened. Notice the sound pressure level now drops to 55 decibel, a drop of 10 decibel. So with the higher intensity now appearing at the edge of the windows, it's no longer the majority of the noise intensity coming from the center of the window. Okay, it has been greatly reduced by 10 dB. Next, we look at some of this non-stationary noise. of a train noise coming from 400 with a frequency range of 400 to 1,200 Hertz. Now with ANC off. So again, the majority of noise intensity is coming through the open windows on the right-hand side of the windows. Now, let's look at ANC on. So you notice that the noise in the center of the window has now reduced quite significantly to only 55 decibel. And the majority of the noise is now coming not through the open windows, but now at the side near to the closed windows. So this work has also attracted several local and international press reportings on the ANC window system. This shows that there's a growing interest from public in this new approach in applying active noise control to open window. I must say that some of the reporters are very creative in coming up with headings such as this one, okay, which is overly exaggerated. So let me conclude my talk by giving some of the key takeaway in this talk. So first of all, I would like to highlight the limitations of a noise control in the ANC windows. So it's limited to low frequency noise control, less than 1,500 Hertz. And the absence of ANC control below the 300 Hertz is primarily due to the implementation of a small loudspeakers array as a secondary source. So we do not want to use a larger speakers so as not to block out the vision, and we also want to minimize the natural ventilations. So we will need to distribute this secondary source across the opening of the windows, and at the same time, we want to ensure the natural ventilation will not be greatly compromised. So it also requires some high-speed processors and low latency electroacoustic components for us to implement this ANC system. Finally, ANC Windows is not a silver bullet for controlling all the different types of noise that comes through our windows, just to take notes, okay? In conclusion, we have successfully demonstrated and reported a proof of principle study in the Nature Scientific Reports. We have successfully reduced the volume of noise transmitted through an open window as seen from the experimentation results and videos. We have a reduction of 10 decibel, which is significant because it reduced the loudness by half and has been achieved in both the space and time average sound pressure level. So with the advance of powerful processing units, low-cost sensors and actuator, and the advanced signal processing and AI techniques, we are seeing that digital ANC technique is becoming a viable tool to reduce the urban noise. So I would like to acknowledge the funding agency for supporting our work. And finally, if you are interested to find out more about this work, please visit this web link for more information and papers related to this work.